Hey Ivan, I wanted to show you these three problems that we were looking at yesterday. They are the same as the recursive function that we looked at. Notice the first one. Let's see if I can zoom in a little bit. So this problem, the one that says a n minus 1 plus 3, starts off at 5, and every time if you do the steps like we did yesterday, a1 is 5, that is when n is 1. When n is 2, it would be, you just have to add a 3 to it. So 5 plus 3 is 8. And then when n is 3, you add another 3 to it. So notice the change is always 3. We are always adding a 3. And since that's a constant, it's a linear function, which you got right. You got all of these right. I'm just not sure if you understood, so I'm just going to go through it one time. So because of that change, which is constant, it's linear. Now, if you look at the next one, this one says a n minus 1 plus 4n minus 3. So what I did was I went ahead and did the same thing that we did yesterday, found all the values for, found a sequence of values. Remember how we did the sequence yesterday? So when a1, when n is 1, it's 5. It starts off at 5. When n is 2, remember it's a1, which is the previous value, plus 4n minus 3. So 5 plus n is 2. So 4 times 2 minus 3 is 5 plus 8 minus 3, which is 10. Then that's the second value. Then the next value, when n is 3, you take the previous value plus 4 times n is 3 minus 3. So if you do that, 10 plus 12 minus 3 gives us 19. And then I found one more value. Take the previous value, 19, plus 4 times n is 4. So 4 is 16 minus 3 gives us 32. Now we go back and look at the differences. So starting with 5 to here's the 5. 5 to 10, the difference is 5. And then we go up a little bit. 10 to 19, the difference is 9. 19 to, what do we have here? 32, the difference is 13. So that's the first set of difference. And then if you look at the second step of difference, 5 to 9 is 4. 9 to 13 is 4. If you do a few more, you'll notice that the second set of difference is always 4. Now you told me that if the second set of difference is always constant, remember yesterday, then it is a quadratic function. So this happens to be a quadratic function. So you just need to find the sequence and find something that will satisfy that to find out what it is. Okay. Now this third one here, I did that here. Notice it says a n minus 1 times 1/3. And again, you got that right. But how do you know it's exponential? You start off with 5, and every time you multiply 1/3. So when you multiply 1/3, so you get 5 times 1/3, you really don't have to do it. A3 is 5 times 1/3, which is the previous value, times another 1/3. So every time you keep multiplying the 1/3, and eventually the 1/3 is how many times we put that as an exponent. So A5 becomes 5 times 1/3 to the power of 3, and then another 1/3. So it becomes 1/3 really to the power of 4. So now you have an exponent, and so that is an exponential function. Okay, so I still haven't done the tree problem. That is again very similar to this. I noticed you just have to keep going with what you have done so far. I think what you have done is right. It is, I would double check the 28, but you need to find the sequence, and you have found the second set of difference. So you said it's quadratic. Now you just have to come up with a recursive function, just like we did here. Notice this is a quadratic function. So you just have to come up with that quadratic function. Maybe you're adding a 2 every time. So it could be n plus 2. You're starting off with what's the start value. Number of triangles is 4. So start value could be 4. And every time it could be a n minus 1 plus n plus 2. So I would try some of those things and see what values you get. So that would be your recursive function that describes, well, that is the explicit function that best describes the relationship above. Remember yesterday we did the explicit function and then the recursive function. So why don't you work on that tree based on what we have seen here, and let me know how it goes. I'm going to try and send you a text and send you this video. Okay.